Thank you everyone for joining. And so today we'll be talking about a geostatistical method for analyzing data from multiple lower diagnostic tools. And this work, I did it when I was a postdoc, partially when I was a postdoc. I think I completed it when I moved to Manchester. So largely, a majority of this work was done when I was in Lancaster University. And it was done under the supervision of Peter Digu, and then we have a collaborator and the task force for global health and other people on the that work together on this. And actually the paper was published. So this talk basically is based on a paper that was published about a few weeks ago, and plus NCD. So I'm just going to focus on what we've done on this paper essentially and try to discuss our method, our geostatistical method, fits into this problem and how we are able to answer the question that they pose to us through our method. So you can see my collaborators there, yeah. So let me quickly give a quick background on this topic. So in poor settings, or let me put it that way, in low resource settings, there's a disease called onchocerciasis, or it's also called river blindness. So that is more intuitive, river blindness, because it's caused blindness and because the parasite that transmits the disease live close to river. That's why they call it river blindness. So, and there has been ongoing efforts to eliminate this river blindness disease. And the way they've done that is through mass drug administration of ivermectin. Everybody's now familiar with ivermectin. Through that's what they do. So they distribute ivermectin tablets to everyone. So in 1991, precisely, so they found out that people, so they just go to a village or to a place, they administer the drug on people just swallow the tablets. They found out that people that are co-infected with lower infection, they suffer serious adverse events from taking the tablet. So when they discovered this, then they started investigating this further that, okay, now we discovered that, okay, people with lower infection are suffering some kind of serious adverse events from it. So at what point? So later, another study in that area also found out that because in the blood, you have the microfilarial parasite, they could measure the level of parasites in your blood. They found out that people with high density of the parasite, they are the ones that are affected the most. And there was also a study that found actually that in regions, so let me just show us this map. So this is one of the early maps that was produced here. So we can see on the left panel, we have the onchocerciasis map. On the right panel, we have the lower infection map. So they found out that area where the prevalence of these two diseases are high, that was where most of the severe adverse events happen. So they find an association between high prevalence of these two diseases and serious adverse events. So, and then, so this has hampered the elimination of river blindness, onchocerciasis, because they have to be careful in the distribution of drugs, especially in areas that has been well established that, okay, we can see the map here. So today I'll be talking about the data that was collected in Gabon. And we can see Gabon here. I don't know if you can see my cursor. You can see Gabon here. You can see something like a very high prevalence, not slightly high prevalence of onchocerciasis there. So the data I'll be using to talk about, that I'll be talking about today was collected in Gabon. And we can see that there's slightly high, we have high prevalence of lower, and then not very high prevalence of blindness, but pretty high in some areas there as well. So, so how do we, what are we doing with this? So basically, we want to assess the prevalence. So basically what they do is that they assess the prevalence of lower infection. So areas where the infection, where the prevalence is high, they don't conduct mass drug administration. What they do is that they test and treat. So they test you if you are carrying high microfilarial density, then they treat you for lower first before giving you the information tablet. So that was how they've done about this. And there are three major tests that have been used in this area of research before. So the earlier maps that I showed, most of the data that were used there use this Raploa test. So of recent, they developed a more advanced tool, which is lower scope test. And then we are all aware of antibody test. That is also pretty recent that they developed that. And I'm just going to go a little bit deeper into what goes on into this test. So the Raploa test is basically a questionnaire. No test is carried out, no blood is measured. They just ask you. So they show a picture. Oh, have you had this kind of worm in your eyes before? If you've had it, they just say, okay, this is a case. If you said no, then that's not the case. That's what they've done. And it's basically to identify areas where the prevalence is high, of loiasis is high. The other one, which is pretty recent, is the lower scope. So this lower scope is a mobile smartphone-based microscope. Basically, they take the blood and then they put it on this smartphone, and it's able to record the number of microvilli in that blood. So, and then they've been using this in different settings. But the problem with this actually is that there are few lower scopes that are available. You can imagine they want to carry out mass drug administration in a particular country, and then they've got probably 100 lower scopes. I don't know how many years it will take them to carry out, to treat people of that. And that is the question they pose to us. They don't, because they have limited number of lower scopes, how can you help us identify areas where we don't need to, where we can safely treat people without having to use lower scope to identify if individuals are carrying microvilli density that is higher than a particular threshold, which I should still talk about later. So that is the goal. They want us to help them identify areas that they can safely just do mass drug administration without anybody, so to say, having serious adverse events, or maybe with probably minimal serious adverse events. Let me put it that way. So, and then we are aware of the lower antibody, it's just antibody, but this one is not really going to say much about what is going on because it's measured current and past exposure. So someone having positive antibody test doesn't necessarily mean, doesn't really tell you much about the prevalence of that disease. So, but this is also used in the field. So let me talk about the Gabon region where this data is collected. So this is southern part of Gabon. And then we have 8 departments. So you can think about departments as districts, basically. So those are the colored ones. They call it departments. And then if you look at the red lines that I have here, the red lines there, I call them pseudo-enumeration units. So I will tell us the reason why I've done that, but basically what I've done basically is to make sure that, because, okay, let me talk about the black dot first. The black dots are the villages that they go and they survey. Those are the villages that they've gone to survey that. But the problem is that, everywhere wasn't surveyed, definitely in those regions, in those departments. And it will be interesting to know, because they don't go to that village alone. They have to go to everywhere to administer drugs onto people. So, and that is where our geostatistical approach actually fits in. So the red line is the Pseudo-EU. And what I've done there is that does not represent any district in Gabon. Basically, I've only sit down somewhere and draw lines on the map, just try to cut it such that I have a population of between 5,000 and 15,000 in all the border in the Pseudo-EUs, which is the red borders, the red partitions that we have there. So basically, that's what I've done. And I'll tell us more about the reason why I have to do this. But obvious reason is because the regions are large, they are heterogeneous, they are particular regions could have a mix of rural and urban setting in a particular district. So that is one of the reasons why we have to come up with a smaller district, basically, to make our inference. And then we go to probably a bit more about the data that we've collected in this setting. So I've talked about three ways that they use in assessing the prevalence: the RAP-lower, the lower scope, and the antibody. So in this particular survey that was carried out, only antibody and lower scope was carried out. So in each village they go there, each individuals, they collect their blood, they carry out antibody test and then lower scope test on each person in the village. So that was so I denote Y1 as a binary outcome. It's just representing presence of detectable antibodies. If it's 1, presence, 0, absent. That is that. And then for the Y2, I denote that as just the microfilarial counts from blood. You can think about that because it's non-negative real number, basically. So it's that 0 to any number, I don't know, not to infinity anyway. It's not that large. Yeah. So so that's what we are. So I denote Y3. So what I did, Y3 there is that if Y2 is greater than 0, then you have 1. If it's 0, then it's 0. So I try to dichotomize Y2 as a binary outcome such that if Y2 is greater than 0, then that is a case, that's 1. If it's 0, then it's 0 for Y3. So we can see how we have come up with this variable Y1, Y2, Y3, and this will be useful for us as we look at the model. So let me quickly talk about why geostatistical approach. Why is our framework useful in this setting, and how are we going to use it? So our approach allows us to capture or explore the relationship between multiple outcomes, basically. So, I said we have the antibody, which I denote as the AB, and then we have the lower scope data. So we can explore the relationship, the association between these two variables in our model. So the second part is that geostatistical approach allows us to capture the spatial correlation between the prevalence. That is, we're just trying to say, okay, if 2 people live close to each other, they are likely to have similar characteristics. That is, things that are close together, they are more related to things that are far apart. And that's what people call the first law of geography. So by accounting for spatial, that is, even if I don't have data in the next village, I can use the data in the surrounding village to inform the prevalence at a particular village if it's closer to the ones they have. And that is where the spatial correlation comes in, that it helps us to predict. And the map I showed us earlier, we can see that we didn't survey everywhere in the district. So geostatistical approach allows us to predict at everywhere in space at any resolution that we like. And again, the lastly there is that it allows us to use relatively small data set. That is, you don't have to call everybody out in the country, and we don't have to make use of the data of everybody to make at least policy decision, basically, to make decision. So that is how our approach fits into this problem. So let's go into the little bit of maths and what we did. So as I've said earlier, Y1, which is the antibody data, which is a binary outcome, we modeled as a Bernoulli distribution, where the probability of when Y is 1, we denote that as rho. So the second thing that we have there is that when Y2 is positive, basically, and that is Y2 given when Y3 is equal to 1, it's just when Y2 is positive real number. Positive real number, we model that as a Weibull distribution with scale parameter, lambda, and then shape parameter gamma there. So, and lastly, Y3, which is the dichotomized Y2, the lower scope data, we model that also as a Bernoulli distribution with probability of Y3 equals to, the case having Y3 equal to 1 to be equals to pi there. So now let's look at the model that we developed here. So the model that we developed here is that we model the probability of being positive for antibody, which is the first equation there. We said that probability is a function of a particular, so mean, I call this mean, and then x of x there. So mean, the way to understand this is risk factor, covariates, that is things that are known about the prevalence of that disease. And then the other part, which is usually called the random effect, you can think about that as the unknown risk or unobserved risk. So the first term there is they're just fixed effects, which are just set a bunch of covariates that you know that is associated with the disease. And the last part is the random effect, which is just unknown risk, or you call it unobserved risk, unexplained risk sometimes. So, and then the second equation is just modeling the mean of the, modeling the scale parameter, modeling the scale parameter of the Weibull distribution. So we try to put a structure on that as well. We said that could be driven by mean and this random effect. So what is going on here is that we put a scale parameter here. So this actually, constructing it this way, where we have, if you look at the first one, we have S naught there. The same random effect, we put it in the second equation. This is how we capture the relationship between these variables, basically. And we're just saying that there's a scaling parameter, which is saying the proportion of this random effect that is common, that of the first equation that is in the second equation. And the last term there, which is S1, we're just saying that what remains after capturing that, maybe there's something that remains that is still spatially structured in a way. That is what we are capturing in the x1 of x there. So, and lastly, our last binary outcome, we also modeled that with the mean proportion of the x naught there, and then what remains after capturing that. And I'm going to speak a little bit about how we model this random effect, the spatial random effect, how we model that. So in this model, our main structure, we used two covariates. There could be other covariates that could be related, but in this case, we've used, even though we have a bunch of them, but we find these two associated with the outcome. The EVI here is enhanced vegetation index, and then this second one is elevation. So we use enhanced vegetation index and elevation as a covariate in our model. And then the X that I've talked about, X0, X1, X2, we modeled that as a zero mean stationary Gaussian process. And how do we do this? So we can define a Gaussian process through its first moment and the second moment. So here we are assuming a zero mean, and then the variance, the way we design this variance is basically we assume a parametric exponential covariance function. You can think about this exponential covariance function. It's just saying that, the correlation decreases with distance. Basically, that's what it's saying that. And we have a scale parameter that regulates, which is phi. The scale parameter that regulates how it goes to zero, how correlation decreases. And this is actually very intuitive, because you can think about that. The farther, if you have two villages, the farther they are to each other, the less the correlation between them. So that is how this assumption of exponential covariance function is very useful. Clearly, there are other, this is just the simplest you could make if you are aware of the Matan class of correlation function. This is just setting a particular parameter there, which is the smoothness parameter to 0.5, but there are other, you can use, if you're in the machine learning world, you know about kernel, you can just think about this as kernel. I think they call this Laplace kernel or something in machine learning world. But this is exponential covariance function. This is a pragmatic choice, definitely. And from experience, we found that even when we try to impose more, I don't want to say more complicated covariance function, it's difficult to estimate the parameters, because this has got two parameters now. By the time you vary the smoothness parameter, which is kappa, have another parameter which regulates the smoothness, then sometimes we don't have information in the data to estimate that parameter. So usually, pragmatically, people just either set, so this is kappa equals to, which is smoothness parameter, 0.5. People vary it. Sometimes some people just fix it at 1.5 and 2.5. And when you assume that kappa is infinity, you are talking about Gaussian covariance function. And then we have the scaling parameter, which is just the alpha 1 and alpha 2 there. which we want to estimate. Looking at this model, it looks complicated because there's a lot of parameters going on there that we have to estimate. So I think the next thing is, let's go to the way we have estimated the parameters of that model. Of course, theta here denotes the parameters that we have. These are just the parameter of the fixed effect, the betas, the scaling parameter. And each S that we have there, each partial random effect that we have there, has its own parameter, variance, and the scale parameter. You can see 3 of them there. This is, it's not easy to estimate this, definitely. So we use Monte Carlo maximum likelihood, and our likelihood function is intractable. It's given in this form. You can see that clearly this cannot be written in closed form. And then the way we have estimated the parameter here is to work with a log likelihood ratio function. And it's essentially taking the ratio of this likelihood by and using your initial best guess of these parameters. So initial best guess. So theta naught there denotes just your initial parameter that you're initializing the algorithm. And then, so what we did there is that, okay, probably what I've not talked about is W. So think about W. Basically, what I denote W are just the random effect of each equation. I have 3 equations. So W1 is the random effect for the first one. W2 is the random effect for the second one. You can see for the 2 terms there. W3 are the random effect for the third equation there. So the main thing we need here in this likelihood is we need to be able to sample from the conditional distribution of W, which is the joint distribution of that random effect, given the data. And that's actually, you can use any MCMC algorithm to sample that anyway. But we have chosen Metropolis adjusted Lagrangian here because we can come up with the derivatives. And if we have the derivatives, this particular Metropolis adjusting, I think the convergence is faster if you have the derivative, and that's why we have used it. But pretty much any MCMC algorithm should be able to sample this. It might take time because the dimension of this is large. So you can think about W grows with your N, number of locations that you have. So if you have 1,000 locations, that's the dimension, basically. So, and then, as I've said, so we work with the ratio of the likelihood function, and that's the expression we have there. You can see theta naught in the denominator, and then theta there. And then we do this. So the question you might want to ask is that, oh, is this identifiable with these parameters that you have? Yes, what we did is just to iterate. So after optimizing it, we estimate the parameter, then we substitute back the maximum likelihood estimates back again. We run the algorithm again until it converges. So with that, at least we're able to satisfy our conscience that it has converged to particular, that our algorithm, optimization algorithm has converged. Okay, yeah, let's look at the parameter estimates. So this is what we get out from the parameter after fitting that model. And I think what would be interesting here to talk about, we know the betas are just the fixed effects, they're just the relationship. What would be interesting is the scale parameter, which is the phi 0, phi 1, phi 2. So the scale parameter. So you can think about scale parameter as the scale of the correlation. So, and intuitive way to think about that is that if you have a data at this village, to what extent can you predict? So can you predict maybe 10 kilometers far away from where you have data, 20 kilometers far away from where you have data? And then, so this scale parameter, for example, theta 0 is 5 kilometers there. So it's basically, if you multiply that by 3, which is 15 kilometers, because I'm using exponential correlation function, we call that the practical range. And the interpretation of that is that the scale at which the correlation goes to 0, close to 0, that is probably 0.05. That is, any prediction you are making 15 kilometers far away from where you have data will be pretty much with large uncertainty. You'll be less sure of what you're doing at that point. That is, you can really borrow strength to predict within 50 kilometer radius of wherever you had. Your model could do well. And that's how we interpret the scale parameter, which And I think that is what is interesting here to know. And that is why when I'm predicting, you will see I've used 2 kilometers for my prediction, that at least if I predict at 2 kilometer resolution, it should be pretty good. So yeah, prediction. How do we do prediction? Now you've estimated the parameters. You want to do prediction. And I'm going to just quote this. Actually, Peter Diggle used to quote this a lot, so I just picked that from him anyway. So he said, the answer to any predictive problem is to write the probability distribution. So if you want to predict, write the probability distribution, then you're good to go. So our predictive problem here, the predictive distribution is given in this form. So if you think about W star at any location in space, so think about W star as the random effect, your prediction of the random effect at any location in space. And here we are using plug-in prediction. That is, after fitting our model, we are assuming that maximum likelihood, Monte Carlo maximum likelihood estimate theta is the truth. Then we are using that for prediction. So you're just plugging that into your predictive distribution as known. Basically, that is what we are doing there. And then once you have the random effect, we estimated the fixed effect before, then what you need is just the random effect. And then that means you can come up with those 3 equations very easily. So we sample, to sample this expression, W star giving the data and the maximum Monte Carlo maximum likelihood estimates. Basically, you just need to draw this first. The W giving Y, that means the random effect giving Y. That guy, we can use the MCMC algorithm that we discussed before. And then when you condition on that, so to sample now, W star, so you can condition on that. You can condition on that W, and then this expression is just conditional multivariate distribution, which is easy to sample if you know the mean and the variance. So that is easy to sample, and that is how we've come up with the prediction of this. So let's go back to our problem that we are trying to answer here. So safety. I told us when I started this talk was that what we want to do is that we want to come up with areas that are safe. We want to tell them that, okay, this area is safe for MDA. We go on and, this area is not safe. So, and the question we will ask is that, what do you mean by safe? How do you know if it's safe? So the way they define, I didn't come up with this definition anyway. So the way the experts has come up with this definition is that they said, okay, if you are very sure that less than 1% of the people in a particular community has at least 20,000 microfluoride per ml of blood, then it is safe. That's what they said. So very sure means if you are 95% confident that less than 1% of people in this community are carrying at least 20% of microfluoride in their blood, then that means it is safe. That is the definition they use to say, okay, this area is safe for MDA. So there are several problems with this definition anyway, and people could argue several numbers here. So I'm not the expert to be debating the numbers here. But from the statistical point of view, what I see that is missing here is that they didn't tell us community. What is the size of the community you're talking about? Are you talking about department, like the way I show us, or Pseudo-EU, or you're talking about pixel level, even at 2 kilometers? What do you mean by community? Community could be diverse. What do you mean? So, and that is one of the reasons why I created the Pseudo-EU that I showed earlier, because I was trying to come up with something homogeneous, a population that is homogeneous in a way. So now that we know the definition of safety, let's look at a bunch of mathematics, what goes on here, and how our model reflects this. So basically, we denote I as a probability of an individual at a particular location X. X here, we chose that as a 2 kilometer grid. So at a particular location X, which is 2 kilometers, the probability that the intensity of the infection, microfilariae in the blood, is greater than 20,000 is given at this equation here, which you can just work this as just the CDF, basically. of the variable distribution could easily come up with this. So the second step there is to compute the proportion of population in a particular community. So I denote community, so to say, as A. So if you talk about A as a district or anything, it could be even the 2 kilometer grid that you're talking about. Here I'm using MX here. MX here is a population density. That is, I'm just computing the average, population weighted average, to come up with the proportion of the population in a particular area with less than 20% microfilaria in their blood. And the definition of safety is just probability that T is less than 0.01, which is what I showed before, 1%. T is less than or equals to, so if probability of T less than 0.01 is greater than 0.5, then we say it's safe. If it is less than 0.05, we say it is not safe. And we impose another constraint that if it's in between, we say we don't know. We don't want to tell you that maybe yes or no. We just say, okay, we don't know. So we come up with these three classes: safe, unsafe, and don't know category. And okay, yeah. So now we know what safe, unsafe. So now our goal is to use data from these two data, Y1 and Y2 and Y3. That is, if you have data on antibody and the lower scope, we use that to make prediction. Then we also say, okay, our statistics, we can use our knowledge of conditional probability. Even if you have antibody data alone, you can use this to predict. You can see that this doesn't depend on Y2 and Y3. So you can also use antibody data alone to make prediction, to declare an area to be safe or unsafe. And then we now propose two-stage strategy. And this is where this is. So what this is that because I told us earlier that lower scope is not so much available, there are limited equipment for lower scope. So we said, go to the field first, conduct antibody tests. When you come back with antibody, our second algorithm here, which is a predict when you have antibody alone, this predictive equation could help us classify districts or communities as safe, unsafe, and don't know. Then when you come back, then we classify with our algorithm. Then our algorithm areas where we have declared as don't know, you go to those areas to go and use lower scope in those areas. So when you go there, you use lower scope in that area, then you come back again, then we now use that to classify. So that's our two-stage strategy. That is, let me recap that again. Go to the phase that use antibody test, come back, we classify as safe, unsafe, and don't know. You go back to the don't know area to go and use lower scope there. And then you give us the data again. Then we use that to reclassify the don't know area. And I'm going to show us the results. So now we have three algorithms. When you have the two data from the field, because from Gabon data, we have the two data. So when you have the two data, when you have antibody data alone, that's the middle panel, and the right panel there is the two-stage strategy. And what we can see clearly here is that the left panel and the right panel, which is when you have both data, when you've collected data and the two-stage strategy, they look pretty much similar. Just looking at this map, this is a prediction at 2 kilometer grid. We can see that the antibody, we can see a lot of don't know, uncertainty in this area. And the uncertainty is higher in this area. But we can see that both left and right panel, they look pretty much similar. So we went further, we said, okay, let's look at how the prediction will look like at our Pseudo-EU level. And if you look at our Pseudo-EU level, we can also see that the lower scope and AB, the left panel and the right panel, they also look pretty much the same. So that is telling us something that our two-stage approach actually what that is. You don't need to carry both equipment to the field at once. You could just use our two-stage strategy. So, and the third one, okay, is the map over the department. So we also do the prediction over the department, and then we can actually see that clearly that the left panel and the right panel, they are pretty much the same. You can see this clearly because there are just eight of them. But we can see the uncertainty, the don't know area when we use antibody alone. So just to visualize this result I've just shown more clearly, so I visualize this as a contingency table. This is the result. The upper panel is for the pixel level. So the left panel is just showing the lower score. When you use the both data and the antibody data, you can see that there's some misclassification here. Yeah. And then by the time we use the two-stage strategy, we can see that pretty much all the pixels are well classified, but we still have very few, but this is just minimal, which is just 11 pixels that is wrongly classified out of all this, about close to 20,000 or something. Okay, 90,000, I think. And then when you look at the pseudo-EU classification that we did as well, you can see that when you use AB alone, you can see some misclassification here. But by the time we use the two-stage strategy, we are able to classify all the pseudo-EU correctly. Lastly, I think I still have a few minutes. So let's look at the simulation that we did. So the simulation that we did here, we are trying to examine a few things about our model, about our approach, what we have checked. So basically what we have checking here with this result is that one, we vary the number of people that are sampled in each village. So we vary that, which is the, if you look at the, what's it called now, the column, look at it over the columns. So the columns, we have 30 people here in this column, 50 people in this column, 70 in this column. So that means we vary the number of people that are sampled in this village, in each village. So let me tell us what goes on in the x-axis of each panel. So the x-axis here is basically showing the number of villages that are sampled. That is, we also vary the number of villages. Sample 48, we check how our model behaves on 96 and 146 village. So let me tell us what goes on in the rows, yeah. So the rows, I have 25% save here, 50% save and 85%. So what we are trying to do here is that we are trying to mimic different settings. We are trying to say, okay, this is the data from Gabon. What if it's another country that has probably different prevalence level? How would our approach behave? So we vary that over when we have 20%, 25% of the EUs that are safe, 50% of the EUs that are safe, 85% of the EUs that are safe. So it's basically checking it to different epidemiological settings, how the model will behave. And on the y-axis here, these are just a metric that we use to evaluate our model. Basically, we are checking the proportion of the EUs that are classified correctly. So, and there are so many things on this plot, but what we see, what is clear here is that when we vary the number of people in each village, that is, if you look at it over the columns, when we vary the number of people in each column, the number of people sampled in each village, we notice that the difference is not that much in the accuracy. If you look at the y-axis, the difference is not that much in the accuracy. But by the time we vary the number of villages that we sampled from 48 to 69, we can see that the accuracy, it's a clear change in the accuracy. You can see that. And this is basically telling us that you gain more when you go to visit more villages than when you sample more people in each village, which actually makes sense. And even we can see, when I was talking about different epidemiological settings, we can see what is going on here, that not much difference in the accuracy across the rows of this plot, not much difference going on there. That is, our model, the accuracy or the precision of our model, it's pretty much the same, probably will remain the same. It's not depending on, it doesn't depend on the prevalence of the lower in that particular setting, basically. So that is what that is showing us. And yeah, I think that is it. So let me just tell us a few things to derive from this talk. So clearly we see that our two-stage approach really work, and that definitely will reduce the time and the cost, because now you don't have to, you only need to carry antibody tests, which is fast, cheap, and everything first. Then the don't know area, those are the areas that you're going to visit. And then we come up with a rough estimate of about 50% reduction in the number of lower scope that you will need in the field using this two-street strategy. And then from the simulation, clearly it shows that visiting more villages is more beneficial than sampling more people in each village. Yeah, and this work is basically, we still have to validate some of the conclusions we have here. So there's a working pipeline to check our approach in Angola and DRC. These are my references, and thank you very much for your attention.